Right now, massive amounts of encrypted data are being copied and hoarded in dark storage vaults by adversaries. It is a strategy known as harvest now, decrypt later. Classical encryption relies on a specific mathematical hurdle, the difficulty of factoring massive prime numbers. On a traditional computer, this process takes thousands of years to complete. That math holds up against standard processors, but a formula called Shor's algorithm provides a shortcut. It allows a quantum computer to solve those same prime number problems in minutes. This timeline plots the projected growth of quantum bits, or qubits, from 1,000 in 2023 toward 20 million by 2030. Measured against a standard 10-year data shelf life, the overlap zone reveals where data harvested today becomes readable by the hardware of 2030. This threat isn't a future event to prepare for. If you are transmitting long-term secrets over the open internet today, they are already effectively compromised. Moving away from classical standards forces the cybersecurity industry to choose between two deeply compromised paths. The first route is post-quantum cryptography, or PQC. This approach attempts to outsmart quantum machines by migrating to significantly more complex math equations. The second route is quantum key distribution, or QKD. Instead of math, this relies on building entirely new physical networks governed by the laws of quantum mechanics. Organizations are forced into a specific compromise. They can choose a code-based transition that maintains global reach but remains mathematically vulnerable, or they can invest in physical infrastructure that is theoretically unbreakable but operationally restrictive. If you take the software route, post-quantum cryptography uses advanced lattice-based math structures to confuse quantum processors. The main advantage is deployment. You can push PQC out as a software update over our existing internet routing hardware and optical cables. But there is a performance cost. This diagram compares a standard AES-256 data packet flowing through a pipeline against a bulky PQC packet, like Crystal's Kyber, clogging the same system. Because these keys are larger, throughput drops. Servers handle much higher processing loads to move identical information. And because PQC is still rooted in math, it carries a long-term risk. A future undiscovered quantum algorithm could theoretically crack these new equations. Choosing PQC means trading absolute future-proof security for the practical necessity of keeping our current physical internet intact. Quantum key distribution abandons math entirely. It utilizes the BB84 protocol to transmit entangled photons over dedicated optical fiber lines. The advantage is certainty. Relying on light's physical properties, security is strictly guaranteed by the laws of nature. This schematic illustrates the physical mechanic. As a photon travels between two nodes, any attempt to intercept or observe it instantly alters its state, immediately alerting both the sender and the receiver. This level of certainty requires immense investment. The specialized chips and routing hardware to handle these photons cost hundreds of thousands of dollars per installation. It also faces severe physical limitations. Transmission ranges max out at roughly 10 miles before requiring middle nodes, and network speeds average roughly 1 megabit per second. QKD achieves perfect security, but the financial cost and physical constraints make it impossible to use for the global public internet. The challenge is even greater for decentralized networks that cannot easily mandate user software upgrades. Take Bitcoin. Roughly $74 billion is currently held in early P2PK wallets that are exposed to future quantum theft. This flowchart outlines Defense BIP 361, migrating users to quantum-resistant addresses. It splits the network, upgraded versus unupgraded. The penalty is absolute. Phase B invalidates old signatures, freezing billions in dormant funds. Without seed phrases, users lose assets forever. This proposal has triggered fierce backlash. Opponents argue it violates core principles, like decentralization and free, unrestricted access to one's own funds. Upgrading to quantum safety requires agonizing choices. These networks must weigh discarding their ideological foundation against the risk of total financial ruin. The quantum transition comes down to a single rule. Physics beats math in absolute security, but math beats physics in scalability. This matrix chart plots the optimal decision paths. If you are an enterprise or SaaS leader relying on the open internet, PQC is the only viable path. If you fall into that group, you must plan for slower processing speeds and begin budgeting for significant increases in memory overhead now. For government entities and critical infrastructure protecting state secrets over short distances, absorbing the hardware cost of QKD is mandatory. Relying on software math to protect state-level secrets is a temporary shield, not a permanent cure. There won't be a singular quantum apocalypse where the entire internet collapses at once. The transition will be a slow, expensive migration process spanning the next decade. Encryption protocols won't simply stop working on a specific Tuesday morning. Delaying an upgrade path means the information transmitted today is being archived by adversaries, waiting for the hardware that can finally read it.